here. Okay, so welcome back, everybody. And I hope you had a great start of the week. What I want to do today is to do a kind of mix of using both the Jupyter notebooks. So there will be a mix of slides and whiteboard at the same time. And but before we move on, I just wanted to give you some of the kind of basic messages. And for those of you who had the possibility to be at the lab sessions, you've probably seen that we have discussed the project. So if you click on the Jupyter book and you scroll down the page here, you will find the project and also the exercises for this week and the previous week. And these exercises are so tailored that you will be able to reuse them when you solve the project. Now, the thing I wanted to discuss in more detail today is about some of the interpretations of Ridge and Lasso regression. And at the same time, we are going to look at these equations and look at some simpler cases so we can gain some kind of understanding of what they actually mean. And when we are done with that, we are going to dive into a statistical interpretation of the results. So I told you in the beginning that this course is a kind of mix of linear algebra, which many of you have seen, the statistics, which many of you may have seen less of, and then clearly the optimization problem with the convex optimization and all that, which follows this, and then clearly the applications to specific cases, developing algorithms and applying these algorithms to analyze data. So that's a kind of basic philosophy here. And it allows you, if you have a background in both statistics, linear algebra, perhaps you will see easier the wood for the trees. But I will try to baby step you through some of the basic elements so that you can actually see the connections between these different fields in mathematics and programming, et cetera, et cetera. So machine learning basically is at the heart is a convex optimization or an optimization problem. It contains lots of linear algebra, and then we have the statistical interpretation. And when you look at textbook like this textbook by Hastie, they often assume that you come from a statistics background. And we will have to bring in some of these elements to help you read in a better way the material. So I'm going to go into the Jupyter notebook first. And because I wanted to also show you some technicalities which we want you to keep in mind when you're developing your own code. There are many small pitfalls, and some of these are pretty boring because not all the instructions and manuals about different libraries are clear enough. So sometimes you can waste some time in just figuring out what am I supposed to do. And one of these things, one of these topics which always confuses us in the beginning is about scaling. And this is one of the things I wanted to mention because I revised a little bit this week's slides and brought back this material about scaling, which you also find in the Jupyter book. So there is a section in the Jupyter book which I recommend reading when you start looking at the project. And it's under this resampling methods, which we will cover in more detail the next week. But there is a section which is called 5.6 on rescaling of data. So this is a topic which asks for confusion in the beginning. So I will try to say something about that, but please feel free to read through it and then come back with questions. So if you get confused in the beginning, it's most likely not your fault, but this is simply because this is a topic which takes some time to digest. In particular, also because some of the libraries which we have, like scikit-learn with Ridge and Lasso, it's pretty common to take out the intercept. And that has often some kind of default scaling in it. And that can confuse us quite a lot. So I just wanted to step you through these details. But let's go back to the material which we have this week. And as I said, I'm going to run a little bit through the Jupyter notebook. And one of the things which we did last week was actually to use the singular value decomposition. And hopefully everybody has gotten this kind of hint for solving exercise 1B this week. So if somebody hasn't gotten it, I sent that by email. It's also uploaded on the Discord because I created some confusion last time, and hopefully that note is able to recover the right content. So the thing we did was to use this singular value decomposition, which allows us to decompose a matrix in terms of two orthogonal matrices and a so-called singular matrix, which contains the so-called singular values, which are always positive. And we used that to demonstrate last week that this quantity here, which is a matrix, leads to a matrix which has only positive eigenvalues. So that matrix which you see X transpose times X is the one which we use in ordinary least squares to find the optimal parameters beta. These optimal parameters suffer from the fact that if you cannot invert that matrix, if that matrix is not invertible, then you cannot solve the equations. And in most applications, the columns in this matrix X, your design matrix where you put in your data with all the features, is something which may have strong dependencies between different columns. And that will very likely lead to matrices which are non-invertible. And the standard trick, as we mentioned, was actually to include just a matrix element along the diagonal. And that matrix, that element along the diagonal cures the invertibility problem. Then we can invert the matrix, but then we are solving another problem. So the other things which we did last week, and which you had in one of the exercises, was to show that the second derivative of the ordinary least squares, or the mean squared error, gives you this equation here. That equation is an equation, as we saw with the singular value decomposition, is an equation which leads to positive, when you diagonalize that matrix, to positive eigenvalues only. That leads to a convex problem. So the matrix we want to optimize, or the problem we want to optimize, the mean squared error, is a convex optimization problem. So there is a minimum and a global minimum. And that follows from the fact that this matrix, which is the second derivative of the mean squared error, has only positive eigenvalues. And we proved that last week using the singular value decomposition theorem. So that was yet another thing which is important for the analysis. And this follows from this analysis here, because the singular values, when you perform a singular value decomposition, they are all positive, except for those values which are zero, which represent singularities in a matrix. So that was one of the things. The other thing which is important for us a little bit later is the fact that the matrix which we get, the second derivative of the mean squared error, is also proportional to the covariance. And the covariance in the data is often used to find which degrees of freedom are correlated or not. These are also things we'll come back to. So what you see now with the ordinary least squares and this simple expression for the mean squared error, we can actually start catching many, many birds with just one stone when it comes to a kind of understanding of what is going on. So I will try to guide you through some of these things today. And in the beginning, it may not be fully clear, so please come back and ask. Now, the thing which you also had in the exercises this week, so if we scroll down here, so I'm just going to go through that one, because this deals with the singularities of the matrix and how to cure them, is the introduction of what we call ridge regression. So let me say some few words about that, so we have everybody with us. Now, we optimize the mean squared error. That is just one possible cost function. So when you go through the literature and you search, or you just search online for cost/loss functions, you will find tons of different functions. So we started with the mean squared error because that gives us nice analytical expressions for many quantities. But there is nothing which hinders you to devise something different. So what you could say now is that you could actually devise a function which looks like this, which is the one we introduced last week, which gives us ridge regression. Now, in the exercises for this week, you can then show that when you optimize this function which you have here, this one, when you take the derivative of this function with respect to the parameters beta, you actually get this expression which you had here. So this was one of the exercises we discussed yesterday and on Tuesday. Now, so what you actually do by introducing a new function you want to optimize, you get this equation which you introduce by cheating, by just adding an element along the diagonal, which is a positive element, okay? So you can view this in two ways. One, I have a matrix which I cannot invert, I cheat, I just add a small element along the diagonal, I can suddenly invert the matrix. Alternatively, I can develop a new cost function which I want to optimize, and this new cost function is given by the addition of this term here. Okay? So keep this in mind that you are free to define the optimization problem you want. Okay? Now, when you have optimized and you found the optimal parameters, what you can do then is to go back and use your model and then estimate whether your model is a good one or bad one. And then you will typically calculate the mean squared error, even if you didn't optimize the mean squared error. But the mean squared error then functions as a way for you to assess if the result is good or bad. And you will see in the project that you're also being asked to calculate the R2 score, which is another way to assess the quality of the model. So keep that in mind that even if you didn't start with the mean squared error, you use that one at the end as a way to assess the quality of your model. Any questions? So maybe I'm saying this in a slow way, but it's in the beginning, we are throwing many concepts at you, and sometimes it's difficult actually to figure out which one is what and is doing what. So the thing is that you can choose functions like this as you want. Now, later today, in the second lecture, we are going to link this with a statistical interpretation. And you can then, using a theorem, which is called Bayes' theorem, which I said is like Pythagoras in geometry for statisticians, you can actually show that you can derive the same equations from a probability distribution, which involves a distribution for the parameters beta. And that's pretty neat. So that gives us a deeper interpretation of what is going on. But what we are going to do now is simply to play around a little bit with some simpler examples. And hopefully that will illustrate what kind of differences we see between these different methods. So when you use the ridge regression, you get an analytical expression for the parameters by taking the derivative of this function, which you see up here. If you use Lasso, you get a non-analytical expression and you have to solve it numerically. But we are coming back to that. So let's switch back to the whiteboard and look at some simpler examples and see if we can gain some deeper insights about what's going on. And then we're going to move over to some other applications and implementations of the Ridge and Lasso regression. And we're going to use these simpler cases to try to develop your insight about the different methods and what you can expect when you run a calculation with them. So keep in mind now that you actually are setting up another problem to optimize. And as we mentioned during the lab sessions, the it's common, but we will not do that in the project. It's actually common to put a constraint on these parameters. That leads to an optimization problem with constraints. And for those of you who have gone through things like Lagrangian formalism, Lagrangian multipliers, and things like that in mathematics courses, that means that you will actually define this function, which you have here to optimize, as your Lagrangian with some constraint on the parameters beta. So how many of you remember something like that or have seen it? So some of you have gone through the Lagrangian formalism. So you see now the problem with us as a group is that we are pretty heterogeneous. So sometimes I hope you can live with this kind of overarching view on things and perhaps not remind you of all the details behind some approaches. But if you want more details, we can always discuss these during the lab sessions. Okay. So let's go down to some simpler cases here. And I'm going to switch back to the whiteboard so we can actually elaborate these simple cases. This was meant as a kind of repetition of what we did during the lab sessions and last week. Any questions so far? Okay, let's switch over to a simpler example here. So we have assumed that we have these equations for ridge regression. So we have defined a cost function, a C of beta, which is now given by 1 over n. And then we have a sum over I, 0 up to n minus 1. And then we have our model, or data minus the model squared. This is a standard mean squared error. But then we add this term lambda, which becomes a parameter, and we have a sum over the features which we have, or the unknown parameters which we want to define, and we have p of them. So this is beta j squared. This is the function when we just write it out in terms of the specific quantities which we want to calculate the derivatives of. And just to quickly remind you, and this allows me also to introduce a notation here. So this y of I tilde is given by our model. So we are making a sum over xij, the matrix elements of the feature matrix, times beta j. And I'm going to use a kind of more compact notation. So throughout the lectures here, and this follows an article which we also have linked to. So I'm going to write this as an X, and then I'm going to put a star here. It looks like an odd symbol. So I'm just going to rewrite it in this compact way. So when you see this star with the X multiplied with beta, that means the summation which you perform. So this is the matrix multiplied with a vector. And we have a model where we simply have assumed that y tilde is given by this matrix X times the optimal parameters beta at the end. Now, when we now take the derivative, with this quantity, the thing you have to keep in mind, so when we take the derivative, the first term is the same as we got when we did ridge in our ordinary least squares. So we got -2 divided by n. And then we had this matrix X transpose times y. So now I'm just writing these out as vectors and matrices. This is what we did last week in the exercises for week 35. And then we have the next term, which now simply gives us a +2 times lambda times the vector beta. You can write out individual components and transform this into a vector, or you can just stay with the matrix vector notation here. Now, the next thing you do then is obviously you want to drive this to 0. And you multiply away the factor of 2, obviously, that disappears. And then you have a factor of n, which you just bake into the constant lambda. So you multiply away this one, and what you get then is x of transpose times y. You move this over to the other side, and then you would have a term which goes like x transpose times x times beta. And then you have a minus. Actually, it's a plus here. So plus, and then you have a n times lambda times beta. And then what you would do then is just simply redefine this to a new value of lambda. You could call it lambda tilde, and then you just call it lambda again. So no, these are just dummy variables, right? And you can call them whatever you want. So I hope that didn't give rise to confusion. And when you then set up everything, you end up with an equation where you have the optimal parameter, which is given by this matrix, x transpose times x, but now you have plus a lambda. And remember now that this matrix has dimensionality p times p, and this matrix here has dimensionality also p times p. And previously you had just lambda, but lambda is just a constant, is a scalar, and you can always rewrite that one as a quantity multiplied with a unit matrix. And this is a matrix you want to invert, and that gives you x transpose times the value y here. So this is a problem since lambda, as we will see later, is a positive constant. So right now, I'm just stating that lambda is positive. After we've gone through the statistical interpretation, you will see why lambda has to be a positive constant. So the matrix x transpose x is a matrix which is positive definite. And we add this parameter lambda, which means that the problem now is a problem which can always be inverted. So ridge regression is a painless way of doing things. It will always give you results. Now, what the results means, another thing. So let's look at a simpler case now. And the simple case which we are going to look at is the following. So simple case to develop a kind of insight. So in this simple case, we are now going to assume that this matrix X is just the identity matrix. So this number 1, which sometimes you will see that as an I, this is my way to represent in my clumsy writing the identity matrix, okay? So then you have only ones along the diagonal. So what I'm going to do now is assume that that matrix X is just given by a standard unit matrix. That means that my model in that specific case, it means that y tilde is simply equal to beta. And I'm also going to assume in this case, just for the simplicity, that P is equal to the number of n. So that X is a square matrix of dimensionality n times n. And I simply assume that it's just equal to a matrix given by the unit matrix. So that means that y tilde is beta. And it means that every y tilde I is equal to a beta y. So when I then do ordinary mean square, my standard ordinary least squares, that gives me a cost function which is given by c beta of 1 divided by n, and then I have a sum over I 0 to n minus 1. I have my data which I want to reproduce minus beta of I squared. That's pretty simple. Even I can solve that problem. And that means that the results which we have, the y's, are just given by the betas. So you see immediately that the optimal model, when you do the calculations, when you take the derivative, and we don't need to do that here, that is simply going to give you, this model here, will simply give you that y of I is equal to beta of I. So let's take ridge regression. So when we minimize, so this is from the minimization, minimize with respect to beta. Now let's bring up ridge regression. So if we do ridge, what we have now is a C of beta, which is equal to 1 over n. And I have this sum, I equals 0 to n minus 1, y of I minus beta of I squared. plus this parameter lambda, and I have I equals 0, and it's the same summation, and then I have a beta of I squared. Then I take the derivative. So if I take the derivative here, I have this dc of d beta of I. That gives me minus 2 over n, and then I have y of I minus beta of I. Pretty obvious, should be. And then I have plus 2 lambda times beta of I, and that's going to be equal to 0. And then I multiply away 2 and multiply away 1 over n, and then I just redefine lambda as n times the previous lambda, and then I just call it lambda again. So that gives me that my beta of I, the ridge, is equal to this y of I of 1 plus lambda. So now it's different from what we had with ordinary least squares, which simply says that y of I is given by beta of I. Whereas in this case, what we have now is that the optimal parameters, so these are actually the optimal parameters. Now the optimal parameters are given by this expression here. So that means that when I tune lambda, I'm going to get a quenching of the values of beta. So what happens here is actually that when I put in the ridge, I'm actually doing a kind of shrinking of specific values. So the next thing we can do then is to do the same thing with the lasso regression. So if I do lasso, which I never remember what's the, this is a shorthand for, what is it? Least squares, shrink approximation, something. I never remember what it stands for. If somebody remembers it, I mean, please feel free to say it. You can actually Google it. I never remember. It's too many words which are brought together into one. Yeah, say. Could you say it again? Yeah, least absolute shrinking and selection operator. Yeah, this is a kind of obvious selection of words, which is easy to remember. Anyway, so that's the. I never remember. I have to look it up every time. But this is just you adding to your cost function, which was the mean squared error originally, a new function. So you're optimizing a new problem. As p as n minus 1, and then we have y of I minus beta of I squared, and now we have plus lambda, and this has a sum over the absolute values of beta here. And then we have to calculate the derivatives of the absolute values. So when we calculate the derivatives of the absolute values, this is going to give us a result which is going to look like as follows. So we will still have this minus 2 over n and y of I minus beta of I. But now I have to take into account this absolute value, beta of I, no, sorry, not beta of I here, but it should be in the denominator. So this is beta of I divided by beta of I. Now, the problem here is that this quantity is not defined when beta is equal to 0. So what I can do next is to redefine this lambda. I multiply away this n, and then redefine my lambda, get rid of the factor of 2 as well. So it just redefines lambda. I guess I don't need to go through that step, right? So I just multiply away, and then I have a factor of n divided by 2 in front of lambda, and then I just redefine a new value lambda, because lambda is a parameter which we are going to play around with. So that means that when I set it up here, I'm going to get this beta of I. When I do the math here, I get the following. So I'm going to get something which looks like this. I'm going to get y of I minus this lambda divided by 2 if y of I is larger than lambda half. And then I'm going to get y of I plus lambda half. So lambda is a parameter. If this y of I is less than minus a half, and 0 if I have y of I less or equal than lambda half. It's actually not so difficult to see that. So this simple case which we have here allows us to make a plot. And this plot is something which hopefully can give us some insight about what is going on. So let me make a plot when you guys have been able to write it down properly. You also find this in the lecture notes, just to remind you of. So every derivation now is actually in the lecture notes as well. Okay, if I change page, is that okay with everybody? Okay, so we can make a plot then. So suppose I plot now my values. So I have a beta of I as a function of y of I. And I know that ordinary least squares, so this is actually the same for every output which I have. So this is my ordinary least squares. It should be a straight line. So please apologize my drawing capacities and capabilities, which are pretty limited. And then, so let's just put that as a -1. We have a 1, and we have a -1, and we can have a +1 here. And then if we do ridge, that's going to look like something like this, which will depend on the value of lambda. So ridge has a quenching factor. So when I have this lambda, you can see now that I can actually reduce one of the parameters beta. So beta gets reduced. That's a very important feature here now, which we will come back to. So what you're seeing is that you can actually take away some specific values of beta. So this is for a simple case where we assume that the design matrix was given by the identity matrix. And now you have a global shrinking on all the parameters beta. So you can actually drive betas to 0. In ordinary least squares, you're not doing that. So if you now plot the ridge on the other, no, lasso on the other hand, so let's just give that a different color here. So when you do that, what you would get then is something which looks like this. And this would be your lasso case. Now, lasso behaves differently. And it behaves differently in the sense that you have regions where you can shrink the parameter to 0. And you have other regions where it's not 0. So let's go back to the equation. So this is just a simple case, which is meant to illustrate the kind of shrinking you can do on the parameters by tuning this parameter lambda. So this is just a simple case. So let's go back to the equations and some examples. And through the Jupyter notebook here. So if you go back to the equation which we started with, what you're doing now is to optimize a different problem than the ordinary least square. So you have this parameter. And depending on the value of this lambda, you can actually put more emphasis on the second part. That will give you a different fit. So this second part lambda is something which now can play a very important role in screening away some specific terms. So what I wanted to also say is something which is now linked with the exercises which we had in the singular value analysis. Now, this equation here is an equation we have to be a little bit careful with because we cannot use the orthogonality or unitarity here because we have reduced the dimensionality of the vectors in the matrix U. So if so U is a, as you can see here, is a matrix which is orthogonal. So in principle, this should just say that the Y model for ordinary squares is the same as the data. But when we do the singular value decomposition, which is also the thing we discussed last week, and you have an exercise 1, then we're actually reducing the number of components in this matrix. So you're projecting out specific features of Y. So this acts as a projection where you don't have all the original elements in this matrix U. And when you go to Ridge, and this was one of the exercises, what happens here is that these singular values, which you have, they can actually, this expression which you see, can function as a way, depending on this parameter lambda, where you shrink away some degrees of freedom. So each P here represents one of your degrees of freedom in the design matrix. Now, if this singular value, which is the eigenvalue in a sense for this matrix, the X transpose times X matrix, if these singular values are very small and this lambda is large, this is a way to reduce the number of degrees of freedom. So by tuning lambda, you can actually drive a specific degree of freedom to 0. It's a way to get rid of degrees of freedom. And let's now practice a little bit. And there are also some hidden gems in here, which we can interpret easily when we've gone through some statistical properties like the variance of the parameters beta. That quantity you see here is inversely proportional to the variance of the parameters beta. And this is going to have an importance for us when we analyze what the results actually mean. Yeah. The parameters beta. So this sigma, which you see, the singular value, which is the singular value of the matrix X transpose times X. So let me just mention this immediately. Let's go back. And this is a thing which is important for the understanding of what happens. So let me just put this up here. This is something we will discuss a little bit more in detail a little bit later, but let me put this up. So one of the things we found is that these parameters, sigma j squared, they are the singular values, or they actually the eigenvalues of X transpose times X. Okay? These are always positive. Now, what we are going to show in one of the exercises next week is that the variance of the parameters beta, when you use ordinary least squares, variance of beta is actually proportional with X transpose X inverse. And that's a very, very important result, because that means that the variance of the parameters beta is inversely proportional with the variance of the parameters beta. So when you're looking at a model which you're fitting, what you will have is that the model you have developed, Y, which is now given by this linear relation between beta, that has a parameter beta where it could have a beta of I plus minus the standard deviation of this parameter beta of I, where this standard deviation is actually the square root of the variance. So this STT of beta of I is given by the square root of the variance of beta I. So this is something we will show in an exercise next week. These parameters are actually inversely proportional with this sigma I squared, the singular values or the eigenvalues of this matrix X transpose times X. So that means the following. What we want to have when we make a fit, we want to have parameters beta which don't vary too much. Because if they vary a lot, that means that the prediction we make will also have huge variations. So think now of, so this is a small digression, which is preparing for the statistics discussion. So suppose now we have made a fit of some data. And these are the data points. And we have a model y tilde of x times the optimal beta. Now, these parameters beta, they have a variance and a standard deviation, so they vary. It's not given by beta only, but it has a variation. So that means that each beta here has a specific parameter. So that means that the prediction we make, if we now label the prediction with the blue points, so we could have a band which goes like this, because we have a model where these parameters here have a standard deviation. So we can make a band which follows the standard deviation of the parameters, and that gives us a prediction we can make with within a certain confidence interval based on the standard deviation of the parameters. This is us presenting the errors, which is invaluable. So when you make a model, if you cannot present the errors in the model, many people will say, what's the validity of your model? So when you now can calculate in ordinary least squares these variances analytically, that is an invaluable result. Because then you can tell your friends in the next party you are going, next Friday, for instance. I think that's the reason nobody invites me anymore. But what you can say then is that I have a model, the red stuff, which lies in an envelopes around the data points. And this is my best model I can make for you. And it makes this prediction with these errors. Now, what you don't want is that these errors are huge, right? So you would like to have it within, let's say, a confidence interval, 95%, something like that, with a pretty good confidence where you say, I'm confident that within 95%, my results are good. That's one possibility. So when you then go back to what you have here, this parameter becomes very important. This is variance, because when you then go back to the simple interpretations we made in these models, in here, since this is inversely proportional with the variance of the parameters beta, you can actually shrink away some of those parameters which have large deviations. And that's extremely useful. So let's see that in examples, okay? And I'm going to step you through some implementations of this, and let's take a look at it. I want to go through an example which we have below here, which contains a polynomial fit. And then I'm going back to the other example a little bit later. So in this polynomial fit, what I have now is a function you've seen zillions of times. It's this x squared. And then you have a standard polynomial fit here. And I'm including the intercept in my fit. And what I'm doing is also to make a lasso and ridge regression where I include the intercept. So this data, which you're going to see now, are not scaled. There's no scaling. I'm including the intercept. And I'm running with, so this simple polynomial, I'm fitting a second order polynomial with a second order polynomial. So it should be pretty good, but I have some noise, which can be large. If you now look at my values of lambda, I've put up an array of lambda, which goes from 10 to the minus 4 to 10 to the 4. And I pick 100 values. So lambda is just a tuning parameter now. And let's see what happens when I now run this calculation. So I make my own ridge here. I do the lasso calculation, so I keep the intercept. And then I write the prediction with ridge and with lasso. I calculate the mean squared prediction with lasso, training, and the standard prediction for the test data. So you see I have test data and training data. So if I run this calculation now, you will see something, and now it should be running, which looks like this. Now, what is going to happen here when you look at this calculation is now I have this is a parameter, it's 2, it's not exactly 0 because I have some noise. And this is a training with standard ordinary least squares. And then I'm running it with Lasso and Ridge. And what you see here now is that for very small values of lambda, this is 10 to the minus 4 on a log scale, we get basically the same result. But then at a certain point, Lasso reaches a plateau. And this is the case where this parameter lambda is now zeroing out all degrees of freedom, all the values of beta, yeah? That's a question. So I just wanted this to show you that my ridge regression is also going to flatten out, because ridge regression suppresses with 1 divided by this singular value plus lambda. So if I make this lambda larger now, so let's just run it. So if I now run it to 10 here, what you will see then is that the ridge is also going to flatten out. And you see that here. So that means that in this specific case, what happens is the following. If we go back again a little bit, what is happening then is that in your fit, the term which is dominating is this term here. And it's driving the parameters beta, which are relevance, to close to 0. And let's now make a polynomial fit and a slightly different polynomial fit, but let's try to redo this now with a simpler case. So let me try to go back a little bit. And we are going to look at the problem where we have a much simpler case. And you can see then how these methods are actually driving the parameters to 0. So in this specific example, which we will take up after the break, I'm simply assuming that my output is given by these values, and my input is a 3x2 design matrix. So I have 2 parameters, beta 0 and beta 1. And then I'm simply going to use ordinary least squares. So when I use ordinary least squares, it's going to give me 2 and 2. That's the solution. When I just plug in that matrix, I invert the matrix and then run the calculation. So just inverting x transpose times x, multiplying with this one, and then I get my ordinary least squares 2 and 2. And ridge is going to give me something which will depend on this parameter lambda. So when lambda is 0, I get back 2 and 2. Whereas ridge has other cases, but let's take a look at the code, and then we take a small break. So in this specific way, in this specific code, you will see now the training for ordinary least squares is free. That's the when you plug in those data, so it's not 0. But then I should actually have it here. So let's rerun it and print these values with ridge. And this is the last thing we will do before we take a break. So when you now start training, you have a training for ridge as well. So this is a parameter beta 0 and beta 1. So they're close to 2. But then I start increasing my lambda, and you see the parameters start now decreasing. And when you go down, down, down here, you will see that this kind of quenching which you have, this lambda quenching, is now driving the parameters to become smaller and smaller. So in my fit now, my mean squared error is actually pretty bad. And I'm driving the parameters beta to 0. And by driving them to 0, I actually have a limit on my mean squared error, which is actually 9.66, which is just the data points. So my data points in this specific case are the mean squared error. When I take this matrix, here it's 16, because I have no model left, because the betas are becoming 0. So I have 16 plus 4 plus 9, so it's 29. And then I have 3 data points divided by 3. So that is 9.66. So that's the threshold mean squared error, which I will get when I'm just driving everything down to 0. So when I look at my calculations here, you will see now that after some specific values of lambda, I'm having parameters beta 0 and beta 1, which are actually getting closer and closer to 0. And then you see this reflected in the plot here, that in the beginning, you have something which is actually free. And then you're quenching the parameters by actually putting more emphasis in your fit to the factor, which goes like beta squared. And that means at a certain point, you're actually driving these parameters almost to 0. Yeah. Yes, yes. We will see that after the break. Then we're going to look at a case where you can find that Ridge and Lasso give better results as a functional lambda. So that can happen. And that is why when what you're doing now is actually you're fitting another function, or you're minimizing another function than the standard ordinary least square function. And that shuffles weights into different parameters in ways which are not obvious immediately. But then when you increase this lambda, what you're doing then is that you're driving the parameters to 0. And then when you calculate the mean squared error, you just have nothing. So tuning lambda means you can get rid of specific degrees of freedom, especially degrees of freedom which can be problematic if you want to get rid of them. And we will see that after the break. So I went a little bit over time because there are some things which I think are important to understand when you tune these parameters, because at the end, machine learning is you setting up a function to optimize, and that function will have many parameters. And some people, as I said in the beginning, get disappointed because at the end you say, hey, I'm just tuning parameters. But this is actually what we end up doing often. The choices of functions we want to optimize are dictated by our insight about the problem. And then with that function, which we believe reflects the problem the best possible way, then the parameters we tune are parameters which we have decided are relevant. Sorry, I went a little bit over time. I don't like to do that. Let's take a break. Let's stretch legs for some 12 minutes and be back at 20 past the hour. Is that okay? Feel free to ask questions. I'm going to put my recording here on. For those of you online, I'm going to put the recording on pause. Okay, so I just wanted to continue a little bit with these kind of interpretations. So just keep in mind that what we are doing is to optimize a new problem. And that problem has the benefit, it can have the benefit, that we can get rid of some specific unwanted features, or we can screen away some specific features. And you saw that from the simple example. And you saw it also from the example which we had with this simple data set as an entry, and then how we could actually just screen away the parameters beta 0 and beta 1 to basically 0 by just increasing this lambda. Now, what I want to do now is to bring in yet another complication. And this is something which we discussed during the lab sessions about scaling of the data, because that, I know, that is something which drives people crazy. So I just wanted to go through that before we jump into the statistics. And next week, we will also discuss these statistical properties together with resampling techniques, which will be very relevant for the project. But let's take a look at this scaling problem. And after we ask this question, we see that we reach a plateau. What is actually happening? What is happening there is that we are driving basically all the parameters to 0. But what we are going to do now is to take a look at another case. So we went through these examples where you can see now you reach a plateau earlier with the lasso, and you see a sharp transition to basically 0 parameters with lasso because you actually screen away before. Whereas ridge regression has a 1 over the singular value plus lambda in the denominator. So that goes in a slower pace to 0. So let's take a closer look now at a technicality like scaling. And I wanted to say a little bit about this, because when you run with scikit-learn or any libraries, and you should also do that yourself, it's common to take away the intercept, because the intercept can penalize your parametrization. The intercept can be large. That's where you cross, for instance, the y-axis. And you want to get rid of that, because that can easily, how to say, penalize the fitting. And when you then calculate the mean squared error, you may actually get a larger mean squared error than you want. So the thing which you need to think a little bit about, and this is how you would do this manually. You can see now that you would set up the train data and you would calculate the mean. This is your training data and the y data. You should also take the mean of the y data. And then you would define your train data as the x train minus the mean, and the y train as y train minus the mean. And then you would fit some model. And we are going to see examples of that. And I will try to tell you why this happens and how it happens and how you can calculate the intercept again when you have fitted without the intercept. Because remember now that if you keep the intercept, that is a column with ones. And if you calculate the mean value of that column, you will have 0. And some of you saw that when you inverted the matrix x transpose times x, because then you would have columns with zeros, and that would give you a singular matrix. So that's a typical case where you should have taken out the intercept. Now, if you then, when you go back, so you train a model, and then you would have an x test, which is now the x test minus the mean. So just keep that in mind, because that's the mean you're taking away from the training data. You should not scale the test data by subtracting its mean, but it's the mean. This word mean in English has too many meanings. So it can mean something, it can be the average, but it can also be something nasty. So the mean values are always mean. Now, they don't need to be mean. Okay, so but you have to, when you then make the prediction, you're making the prediction with the test data, but then you should bring back this mean value. And there are some equations here which I just wanted to go through with you. And I invite you to take a look at this, because this is going to confuse you. It confused me, and I'm not the smartest guy, but you probably are much smarter than me, so probably you will figure out at a quicker pace than I did, but it took me some time to realize this. So if you now look at the cost function for standard ordinary least squares, it's common in basically all applications to take out this term here. Now, when you come to lasso and ridge regression, this is done by default. So that means that this extra term with beta squared, or the absolute value of beta, is done without beta 0. So just keep in mind, if you have a polynomial fit to something, or you have some data which traverse an y-axis, where it hits the y-axis can be a large number. And you want to avoid your fitting being penalized by a possible large number. Now, if you then take the derivative with respect to beta 0, the intercept parameter, then you see now that you can rewrite this. You want to drive this to 0. And that means that beta 0 is just a constant. So this is just a constant. And when you sum it up, this is just n. And then you're left with this number and this number here. And here, I just limited myself to beta 0 and beta 1. So my fitting now is only going to be a fitting with beta 1. And then you see, if I divide by n here, this is the mean value of y, my output. And this would be the mean value over all the elements I have in my matrix, x, for that specific parameter beta 1, which is the one I'm using. So if you then define this as the average value of that specific column for beta 1, and you define the mean value here, you can then see that you can calculate beta 0 after you have done the fitting of beta 1, beta 2, etc., etc. And this would just be given by this mean value for the columns and the mean value of your output variables. But remember that you're doing these operations on the training data. Okay? Just keep that in mind. So when you train, these X's here are the typical and the Y's are the training outputs and inputs. And you see now that you can recalculate in the general case, you can recalculate this beta 0 with the design matrix and all these values beta here. And you can rewrite this equation when you now sum over J0 as simply the mean value for the column you're looking at and multiplied with the parameter which you found when you did the fitting. So this is a way by which you can then recover this specific value. So when you run scikit-learn, like ordinary least squares, Ridge, or any of these methods, it actually does this almost by default. So it doesn't include the intercept. And that means that when you print the coefficients, you won't get beta 0. You have to ask for beta 0. And then it recalculates it. So this is essentially what happens behind the curtains. So that typically means that you would replace your Y with this this absolute value. And you would have this changed parameters now where everything has been scaled. And where the design matrix is scaled and your Y values are also scaled here. And then you would have this Xij, which you see here, would be the Xij, the columns, and you would subtract the mean value. So let's take a look at some examples. So I'm going to skip the first example, but I'm going to show you what it can mean for Ridge and Lasso regression. So if you run a calculation for ordinary least squares with and without the intercept, nothing will happen. You will get the same results for the parameters. But when you add Ridge and Lasso and you take away this intercept, then these factors which you have, these factors with the parameter lambda, they will actually play an important role. So mathematically, these will actually change the values of the parameters you fit. So let's look at this, an example here. And we are now going to look at a slightly more complicated function. And I'm going to have an e to the minus x squared. I'm going to define a polynomial of degree. Let's start with a polynomial of degree 5, let's say that. And you see now that what I'm doing here, now I'm including the intercept explicitly. So I'm running the fit with the intercept. And you see that because this starts with 0. So this is a smart way by which you can set up the design matrix. So in the previous cases, I was actually setting up the design matrix row by row, not column by column, sorry. And now I'm just automatizing it, which is much better than just you having a long, long list of declaration of each polynomial degree which you have. So it's still polynomials, not so exciting. Here I split in train test. So I'm not doing any type of scaling. I'm just using the data as they are. I do my Ridge regression. And you see now I calculate my Lasso. I use actually Ridge with the intercept equal false. And I'm going to make a comparison mainly with the Ridge regression and ordinary least squares. So the ordinary least squares are the results which you will find easily by simply just inverting the matrix. But let's now look at what happens here. So I'm going to print the beta values for this Ridge implementation and also the one for which scikit-learn gives. So let's see what happens now for a set of values here. So one thing you will see here, this is the intercept. This is the first parameter, the second one, etc. And then you see also I have a pretty small mean squared error. So in the beginning now it's pretty small. And then you see that my own implementation and the one which scikit-learn gives give the same results. Now, as you keep moving and you increase this value of the parameter lambda, so lambda goes from 10 to the minus 4 to 10 to the 2, and I take only 6 values. Now, when I increase that, you will see now that if you look at the parameters here, they take a certain value, but now they're becoming smaller and smaller. And as I increase this lambda, you see now that the parameters become smaller and smaller, and some of them now are being driven to 0. So this is the shrinking which Ridge does for you. You also notice now that the mean squared error is also increasing, which reminds us a little bit of what happened before. So in the beginning, you're getting something which will be pretty close to 0, but then it starts increasing. Now, there is another thing I wanted you to think a little bit about here. So this is a case where I didn't add any noise. So I'm having a pretty smooth curve. And you see that in the sense that the parameters, when you go to high order polynomials, they don't blow up. So not blowing up means that this term, which goes like beta squared, doesn't blow up. So order by order, my polynomial, the next terms are not dramatically larger than the previous ones. If I were to add noise, you would see this immediately. And then you could have a parameter for the fourth order term, which is minus 100, the one for the fifth order term, which is plus 1,000. And then when you're summing up, then this term, which goes like beta squared times lambda, can become huge. And that will spoil everything for you. So when you have noise, these are things which can happen. So let's take a closer look at the next example. So in the next example here, we have a, I thought I had plugged in noise. I think I had forgotten to plug in noise here. Now here it comes. Yeah, so here we have it. So this is just a case when I do the fitting. In this case here, I do the fitting without the intercept. And what you would see then is that the parameters which you get then, where I do the fit with and without the intercept. Now without the intercept, then when I'm making my prediction, I have to bring back this mean value, the scaled mean value, which I have in here. That has to be brought back, because else, when you make a comparison with the raw data, you're actually missing the term which is subtracted here, the scaling. So you need to bring that back when you make your own prediction, because else you will get a data which are shifted. Now, in this specific case, you will also see that when I take away the intercept and scale the data, in this specific case, you will also see a mean squared error, which is not impressively larger than one you saw previously. And you will again see that some of the parameters, as you increase this lambda, they are being driven to smaller and smaller values. So they will keep decreasing. And you can see that here, this is 0.06, and now it's 0.01. And then you increase the values of lambda, and then you're driving more and more parameters to 0. And you will also see then that the mean squared error is increasing, as you saw in the previous case. But let's now look at what happens when we use Lasso and Ridge. And we are going now to repeat these calculations, but we are going to have a polynomial which has some noise as well. So when I add noise, I can actually get a large variance in the parameters beta, because now I'm trying to fit not a smooth line or smooth curve, but I'm actually going to fit something which has a lot of noise. And then what you will see is that the parameters beta may actually vary a lot from one value to the next one. So let's take a look at that and keep a polynomial of degree. Let's do a polynomial of degree 6. and let's have less points here. So we do a polynomial degree 6. We still keep the intercept, and we run calculations with both Ridge and Lasso. So I keep the intercept. In the next example, I will take away the intercept. If you now look at the parameters, so this is ordinary mean squared error. These are the parameters I get from the ordinary mean squared error. And this is the lambda parameter. So I increase it from close to 0 up to 10. And the first line, which you see here, this is ridge regression. And what you note is actually that the parameters, they actually vary a lot. From, if you go back again up here, you will see that it prints the prediction from ordinary least squares. And you see now you have a parameter which is 19, minus 126, 320. This is minus 350, and this is 138. So I have data with lots of noise. And that means that when I'm trying to make the fit now, the parameters beta can vary a lot. And that can really cause problems when you now do the Ridge and Lasso regression, because the parameters will be large. So this is with the intercept. Now, when you look at the Lasso result and Ridge result, you see now that these methods, they shrink some of the parameters. And after the few iterations here, you have 10 to the minus 3. You see now that it has actually been shrinking the parameters, which you would get from ordinary least squares to smaller values. And gradually, with Lasso, you have just one which survives. And that means that your mean squared error may look something like this. And it seems that the Lasso here gives a result which is below Ridge. When you compare that with the ordinary least squares, that can also happen, that you get results which are different. And this is the kind of thing you would end up doing when you tune these parameters. So if we now do a larger data set, and we could do a polynomial of degree, let's say 15, you will see that these results will change again. And if we look at the plot, we can get something like this. If we now change to a calculation where we now take away the intercept, and let's see, didn't I have that example here? I thought I had that example. Oops, I think I had an example without the intercept. So let's do that. So let me just take that one away. I thought I actually had that one. I must have forgotten to bring it up here. Okay, that should be polynomial degree +1. And then we take away the intercept. Where did I place this program? I've been confusing myself here because I thought I had the program. Yeah, this is me confusing myself here. I actually had a program which I thought was in the slides this morning. And I had where did I put that one? Okay, let's just run it with true here. So what you may get when you now change and take away the intercept, the fitting which takes place now may be less sensitive to that value. And here I've just chosen let's take more values for this lambda. And I'm not going to print out these results, but because you will see much of the same. But let's do the fit without the intercept. And you may see results like this. So we're now, for these different values of lambda, you are now getting a result with a ridge regression, which actually looks better than Lasso. And then you have a point here where Lasso is doing better. If you then change this region to, let's just change the degree of the polynomial to, let's say 20. And then we take the, and do the training without the intercept and have values of these lambdas, which go from 10 to the minus 4. What you will get then is something which may look like this. So depending on the data set you have and the number of points, you can actually get values for the mean squared error, which can vary from case to case. And it's not given a priori whether mean squared error, plain ordinary least squares, give a better result than Lasso and Ridge. So that means you would need to play around with different hyperparameters, this lambda, and see what gives the best mean squared error and R2 score, etc. But just keep in mind that when you increase this value of lambda, that will penalize your results. And it may drive some of the coefficients to 0. So if you have a lot of noise in these calculations, what can happen then is that these higher parameters, if we now print the parameters, and let's just print them, and do this only for some few values of lambda because it's easier to see. You will see in the beginning that there are parameters which are huge. Can you see that? So this is the lowest case, and this is the test mean square error. So when I use ordinary least squares, I get 0.99. Now, when I am, so this is the close to 1. So when I'm now using ridge regression and Lasso, you see now that when I'm doing the fit without the intercept, as I'm doing, you see now that the parameters are still large and oscillating, but they're not as large and oscillating as they are in ordinary least squares. So the reason why you see these large oscillations is simply because you have lots of noise. When you take away noise, the parameters, the difference from, let's say, 4th order to 5th order will not be that large. So these are things we're going to live with. So when you have these large values, you will also find a large variance. So a large variance for the parameter beta will be quenched by this parameter lambda in the hyperparameter. So there are many things to keep track of. And if it's not too clear yet, I mean, just let me know. But then when you start increasing lambda, so now lambda is equal 0.0 something, you see now that the ridge regression still gives something which is non-negligible, whereas Lasso regression has started to drive many of the parameters to close to 0. And then you keep increasing lambda, and you will see then that ridge regression has almost all parameters to 0, and then you reach here, and then everything is put to 0, the parameters. So that means that when you calculate the mean squared error, you get something which flattens out like this. And that's only the data points which you have the outputs which kick in. Whereas the mean squared error here is actually pretty good. And you see now that the result here goes down to 0.99. And the result which you had with ordinary least squares is close to 1. So actually, you're getting a better mean squared error when you do ridge regression for this data set. And this is something you don't know a priori. So data with lots of noise will often require that you tune these hyperparameters so you find the optimal parameters. So in project number 1, start with just a smooth function. Don't add any noise. And then you will see normally that ordinary least squares is going to give an almost perfect result. Then when you add noise, then clearly a polynomial fit is not going to be the best model. And then you will see large variations from one order to the next order, because your model is trying to make the best possible fit, and then you can get large variations. And this is something which you will see again and again when you're making these fits. And then Lasso and Ridge, they will often drive down to zero those parameters which have large deviations. And we are coming back to that when we've gone through these statistical discussions. So I hope this illustrates a little bit from the numerical calculations here what happens, and also that you can use this sampling and scaling stuff, which we have in the project. It takes some time to get used to what it means. So take a look at the slides and take also a look at what you have in your Jupyter notebook. So what I wanted to do now, and this is actually what I wanted to start with in the lecture, so I'm a little bit slow. I actually wanted to go into the statistical interpretation. And we have things which are going to be relevant for us in the project. And one of the exercises which we have next week, so there's only going to be one exercise next week, is actually you calculating some of these expectation values. So I wanted to go through that, and then we will have to defer to next week the link with a Bayes theorem and what Ridge and Lasso actually mean. So I think this is it doesn't sound like the most exciting topic, but it's a technicality which is important to keep in mind when we perform this kind of fits. So let's go back to the whiteboard and look at statistical properties. So this is the link with statistics, and let's start with clean sheets. So what we have done is actually to define a given output. We have assumed that there exists a function which we don't know, and that there is some noise. This is a basic assumption about the data. You could say, as we said in the beginning, that this is also part of the model. And this epsilon is given in terms of a normal distribution with zero mean value and sigma squared, which is a variance, which we don't know. If you put it to 1, you have the standard normal distribution. So this is the assumption we have made about the data which we have. May not be true. Then we have made a model, and the thing which is important for us now, when we look at, so this is the expectation value of a quantity, of this epsilon. So we know that this follows a normal distribution. So this will be given by x, an integral over the domain where x is defined. Epsilon may depend on x, and then we have some p of x, and this is defined to be 0. So that's the mean value. So this E stands for expectation value. And what we also have is that the variance of this quantity, epsilon, is given by this quantity sigma squared, which we haven't defined. We just assume that that result is non-zero. It could be 0, but we assume that it's non-zero. The next thing we want now is that we have assumed that y is given, y tilde is given by some model which we have made up, and that's given by this matrix x times beta. That's the assumption we made. So what we say now is that this approximates this function f of x. So x uppercase letter is a matrix, that's the design matrix, and little x is a vector. So this is the assumption we have been dealing with. And that means that when we now look at y, we could now approximate y with x of beta plus epsilon. Any large protests against that? Now we want to calculate the expectation value of y. So let's do that. So there's an important assumption X, the design matrix, is a non-stochastic variable. We don't know anything about beta, but we are going to assume that beta now is a non-stochastic variable. And this has some consequences for expectation values. So we have, when we're looking at expectation values, so if we now look at this y of I, we are going to approximate that one with this sum over j of xij multiplied with beta j plus a noise epsilon I, which is the same for all the observations. So all y's have the same noise. It's given by a normal distribution. So the noise is given by identically distributed and independent variables. And they are just given by a normal distribution. So this is a y, and we rewrote this one, this term here, we rewrote it in this kind of compact way, like this x with a star to indicate that we have the summation plus epsilon of I. And now we want the expectation value of this quantity, of y of I. And when we take the expectation value of a non-stochastic variable, that is just itself, plus the expectation value of epsilon of I. This is defined to be 0. So this becomes simply equal to this matrix times the vector. So the assumption we've made about X is that it is not a stochastic variable. You can fix the input to precise precision. There is no stochasticity behind it. So if you're making a survey and one of the entry points is the date of birth of people, that is pretty well determined. Yeah. So stochastic means that it follows a distribution. So, and that you can have a variance in the results. So the non-stochastic variable is something which is precisely determined. And you would say that about your input. So this is an assumption we are making. You could assume that your x's have a distribution. That is possible. Now we're just making the assumption that everything is fixed. So it's like you running an experiment and you fix the voltage. And the voltage takes this value. And you assume that it is not a random variable. Like as I said, if you're making a survey of people, an entry could be the date of birth. And hopefully there is no randomness with when you're born, right? So that means that we can write like that. So this would be the expectation value of y. The next thing you can do then is to calculate the variance of y. We can take y the vector or just y. So let's just keep one specific contribution here. And that is given by the expectation value. And this is the quantity y of I minus its mean value of E of y of I. And we found that one in the previous expression. So this is the definition of the variance. So we know this value. So this is the same as the one you have here. And you can, when you write this out, you can actually show that this is given by E of y of I squared minus the expectation value of y squared. Now, if you now look at the value for y of I squared, then we are going back to the model which we have, and we are going to plug in the model which includes this noise which we have. So that means that when we are going to look at this specific expectation value, we are going to square the quantity which you see here. So let's continue. And if I now look at this quantity which we need to look at, so this is going to be equal to this quantity, and I have xi, and I have this strange notation here, plus epsilon of I squared, minus, and then I plug in the value, and this is beta, so this is just a scalar, just keep that in mind, squared. And this becomes simply equal to E expectation value of xi beta squared plus 2 times the expectation value of xi multiplied with beta multiplied with epsilon of I plus this epsilon of I squared. This minus xi times beta squared. Now the first term, this term here, is going to cancel that one. They're going to be the same. Remember, x is assumed to be a non-stochastic variable. So that means that if we look at these terms, these two terms will cancel. Then, in this specific case, x again and beta are assumed to be non-stochastic. So the only stochastic variable, which we have defined to be so, is the random noise, epsilon I. So that means, and we have defined the mean value of epsilon I. So the mean value of this one is actually equal to 0. So what we are left with then is actually the expectation value of epsilon I squared, which is the same as this variance, sigma squared. So what we are going to infer from that, so we are making an assumption now that we can infer, since the epsilons follow a normal distribution, we are now going to assume that y also follows a normal distribution, but now with a mean value. So y of I is now given by a normal distribution with mean value xi times beta, not 0 anymore, but with variance sigma squared. So that's an assumption which we are going to make. And this allows us, if we have a normal distribution like that, and we will see that next week, that is going to allow us to derive ordinary least squares by maximizing a probability, which is a product of Gaussians. That's another way of deriving the same equation for beta, but starting with a probabilistic interpretation. And then we are going to derive next week Ridge and Lasso using the same approach. So you can actually derive these equations from a probabilistic point of view. Now, the next thing we need for next week, so this is part of the exercise for next week, and it lays the foundation for the statistical interpretation, which we are going to do. So the last thing I'm going to put up today is actually the calculation of this parameter beta. And if you look at beta, that is actually given by the expectation value of x transpose x minus 1 of x transpose times y. And we can rewrite that one in a very simple way in terms of the model which we have for y, which now gives us, so if we replace that with what we have for the model, so that means that we take y and replace that one with the model for y. So we would have x transpose times x times beta. So we are now simply assuming that we can replace this y with the model we have made, because we don't know the exact function f of x. We don't know that function. We have approximated that function with x times beta. Now, and then you see that here, this one cancels this one. So we are just left with the expectation value of beta. And we have assumed that that one is also not a stochastic variable. So that is going to be given by the expectation value of beta. And we normally say that that is something which we call an unbiased estimator. So that means that the expected value is equal to the true value, which is the one we get from the mean squared error optimization. That's normally what we mean by an unbiased variable. Now, the thing which we will show in one of the exercises next week is that the variance of these parameters beta are actually given by the inverse matrix xt minus 1 for ordinary least squares. And that's an extremely useful result, because then we can say what is the standard deviation for the parameters beta. And then when we have a model, we can set up an estimate of the error we have in the model. which is extremely useful. So these are some of the analytical elements which will be part of the project, which you will have as an exercise next week. So I want you to go through that. And I was hoping to reach a little bit longer today, but I thought it was useful to, I don't know if you thought it was useful, but I hope it was useful to see these numerical experiments with Ridge, Lasso, and ordinary least squares. Because it takes time to understand what is going on. And you understanding what goes on means that you can see the pros and the cons of the models. And then next time you're using them, you have a better feeling and confidence in what you can get and what you should get and what you can expect from the models. But next week, we are going to continue along this line. And then we will also discuss resampling techniques. And then you will, in principle, have the basic elements for project number 1. Any questions? Things which aren't clear? Anyway, feel free, use the Discord channel, send me emails whenever you want. Yeah. Yeah. Yes. So you're going to get equivalent expressions here, except that you will have this addition which ridge regression gives you with the parameter lambda. So that means you can actually tune the variance of the parameters. And you will see that next week. Okay. Have a best wishes for the rest of the week, everybody. Take care.